Hello and welcome to Dr. Jim's Structures class, where we do structures by example.
Man's practicing fuzzy math again.
Thank you for tuning in. In a previous video, Dr. Jim introduced the method of joints by analysing this pin-jointed frame. This video will show how to check the hand calculations using LinPro. If you want to watch the hand analysis video, then click the link on the screen. LinPro is a free, lightweight, graphical and easy to use frame analysis program. Dr. Jim recommends downloading a copy of LinPro from the web. Alternatively, get yourself over to Dr. Jim's website at drjimstructures.com and download a copy from there. There's a link to the website in the description. This video assumes that you're familiar with the basics of LinPro. If you're not, then you might want to watch Dr. Jim's introduction to LinPro before continuing. If so, click the link on the screen. LinPro offers both keyboard and graphical input capabilities. We will use graphical input where possible, as it's quicker and less error prone. The analysis starts by considering the units to be used. LinPro's default units are kilonewtons and meters, and these happen to coincide with the units used for the hand calculations, so nothing needs to be done. Next, define the grid, so click the grid button to open the grid dialog box, then set the width to 10 meters, the height to 2.5 meters, and the grid spacing to 0.5 meter. The grid points on the grid are shown as small dots, but unfortunately the colours used and the small size of the dots makes them difficult to see on most screens. Before continuing, a word about computer analysis and the terminology used. LinPro is based on the stiffness method, and the stiffness method is a special case of a more general analysis technique known as the finite element method. The finite element method uses the term node, where LinPro uses the term joint. This is unfortunate because, in the real world of engineering, the term joint has a specific meaning. A joint is a structural connection where two or more independent structural elements are physically connected together. In the mathematical world of computer analysis, a node is simply a reference point on the structure. Nodes are not restricted to joints. For instance, a node could be defined halfway along a structural element. And there's more. The finite element method uses the term element where LinPro uses the term member. In the finite element method, the term member implies a line or stick element, the type of element used to model beams and frames. A line element is just one element from a large library of finite element types, including shell elements and solid three-dimensional elements. And that's without getting into the element types used to model heat and fluid flow. LinPro offers only line elements. To clarify, consider this LinPro model of a continuous simply supported beam. In the real world, the beam would be built from two physical members connected by one structural joint at node 2. LinPro's mathematical model consists of 5 joints and 4 members, or, in finite element terminology, the model consists of 5 nodes and 4 elements. We will mix the LinPro terms joint and member with the more generic finite element terms node and element. Hopefully doing so will simplify your future encounters with more powerful structural analysis programs. To summarize: 1. Joint is a physical connection between two or more independent structural elements. 2. A node is a reference point on the structure. 3. To define a support, a node must be located at the support. 4. A member is a particular type of finite element, a line element, that's used to model beams and frames. This has been a bit of a detour, but worthwhile. Terminology is important. Now, right-click in the workspace and select the joint pointer. Next, add joints by clicking in the workspace. Note that the pointer coordinates are displayed at the bottom left-hand corner of the window. and the coordinates snap to the grid, making adding nodes simple. The node numbers are assigned sequentially by LinPro, starting at 0. The order in which the nodes are defined is immaterial, but Dr. Jim likes A to map to 0, B to map to 1, C to map to 2, etc. Why? Because that's the way he's wired, I guess. Next, right-click and select the member pointer. Notice a dialog box pops up showing that we're entering Type 1 elements. We have not defined any element types, so we are using the default LinPro element. And it will not surprise you to learn that Dr. Jim has produced a video that reverse engineers the default LinPro element. Click the link on the screen if you would like to watch that video. As with nodes, the order in which elements are defined is immaterial. Here the elements will be entered using the fewest number of clicks. Notice that when 6 elements have been defined, we are back at node 0 and LinPro is offering to add another element connected to node 0. This is not what we want, so right click and reselect the member pointer option to lose the piece of elastic, then add the last member. Right click, select the pointer option, then double click to deselect node 3. Next, right click node 0 and select pin support to define the knife edge support at A. Double click on the workspace to deselect node 0, then right click node 4 and select vertical support. We now need to apply the loads. Double click the workspace to deselect node 4, then right click on node 1 and select add load. The add load dialog box opens. Give the load a meaningful name, then enter 40 in the Force X field. Double click to deselect node 1, then right click node 2 and again select add load. Give the load a meaningful name, then enter -100 in the Y force field. The load is negative because it acts downwards, that is, it acts in the negative Y direction. Click apply to apply the load. Have you noticed that there's something wrong with the 100 kN load? If not, pause the playback and have a think. Here's the problem. The arrow points downwards. That's good. That's the direction the load acts. But it has a negative sign. That's not so good. In fact, it's deeply worrying. Logically, -100 kilonewtons acting downwards is the same as +100 kilonewtons acting upwards. If that's not obvious, then please stop the playback and think about it. It's important. What you need to know is the force arrows in LinPro always point in the actual force directions. When using LinPro, negative signs on graphical representations of applied loads and reactions should simply be ignored. LinPro is good, but it's not perfect, and apologies if you've heard this rant before. We've defined the structure, the supports and the loads, so we're good to go. Let's try it. Click the green arrow to run a linear elastic static analysis. It's super quick and LinPro shows the displacements caused by the loads. The deformed shape looks reasonable. Always check this. Next, check the reactions by clicking the R button. Great, they agree with our hand calculations. Now, click the N button to display the axial forces in the members. The results are close to the hand calculations, but they are not the same. For instance, our hand calculations gave 120 kilonewtons compression in the top horizontal member. LinPro gives 117.99 kilonewtons compression. Has something gone wrong? Perhaps it's rounding. What do you think? If you're thinking, no way it's rounding, then well done. The hand calculations were done using 4 significant figures, so rounding could not account for an error of around 2%. What to do next? Any ideas? It's good engineering to apply quick, simple checks first, and we know that pin-jointed frames carrying joint loads experience only axial forces in the structural elements, so click the M button to check there are no moments in the frame. Uh-oh, shock horror, there are moments everywhere. Small moments, but moments nonetheless. Moment and shear usually hang out together, and clicking the T button shows there are small shear forces throughout the frame. Click the Draw Structure button to view the space diagram of the structure. Admittedly, the joints look like they're pinned, but these little circles represent nodes, not pins. To proceed, we need to know about joint connection types. Joint connections is a big subject, but here we need only consider the difference between rigidly connected joints and joints that are pinned. And here's an example of a rigidly connected joint. And here's an example of a pinned joint. When a frame is loaded, the frame deforms, causing the joints to displace and rotate. All members at the joint displaced by the same amount. In other words, the members remain connected. And by the way, that's a good thing. The difference between rigidly connected and pinned joints is to do with joint rotation. If the joint is rigidly connected, all members rotate by the same amount. If the joint is pinned, all the members are free to rotate independently. Of course, joints containing a mixture of rigidly connected and pinned members are also possible. What we need to know is that frame analysis programs assume all joints are rigidly connected unless told otherwise. While building the frame, we did nothing to make the joints pinned, so I've built a rigidly connected frame, hence the bending and shear. Frame analysis programs make pin joints by releasing moments at the ends of members. You should think of a moment release as adding a pin. Let's try to make joint 3 pinned. Click the Members button to open the Members dialog box. Members 2, 3 and 6 are connected to node 3, so it's not unreasonable to think that adding pins, that is, releasing moments, at end 3 of these members will make joint 3 pinned. Select member 6, then click the End Releases button. Notice all 3 types of internal member force can be released. Click the checkbox to release the end moment at joint 3, then click OK. LinPro graphically shows this release by drawing a pin at end 3 of member 6. That's fine. Now do the same for member 2. Notice instead of showing pins on members 2 and 6, LinPro has removed the pin from member 6 and has coloured node 3 grey. Curious what you think's going on. Strange things are happening, but let's carry on regardless. Add a pin to end 3 of member 3. LinPro now shows all the pins we have added and colours node 3 red. Curiouser and curiouser. We all know red is for danger, but what's going on? Let's try to analyse the frame. What could possibly go wrong? Close the Members dialog box and click the green analysis arrow. LinPro throws up a dialog box saying the analysis has failed. The problem is easy to fix, but to understand what's going on requires a little work. Plane frame nodes have 3 degrees of freedom: displacement in the x direction, displacement in the y direction, and rotation. For the stiffness method to work, there must be positive stiffness at every freedom. For example, x displacement at joint 3 would stretch members 6 and 2 and compress member 3. The force per unit displacement is the stiffness associated with the freedom. Displacement of joint 3 in the y direction would generate tensile forces in members 2 and 3, so the y freedom would have a positive stiffness. However, rotation at joint 3 would require no moment because of the 3 pins. In other words, the rotational stiffness of joint 3 is 0, and that causes the analysis to fail. Joint 3 is a mechanism when it comes to rotation. The solution is to remove one of the pins at joint 3. Which pin does not matter, so let's remove the pin on member 6. Notice the display changes. No member pins are shown, and joint 3 is coloured grey, indicating the joint is pinned. Now try clicking the green analysis button. This time the analysis succeeds, and inspection of the results shows moments at all joints except node 3, where the moment is 0. So joint 3 is now pinned. Woohoo! It's logical to think there should be a moment at end 3 of member 6 where we removed the pin. However, consideration of the free body diagram for node 3 shows that for moments to sum to 0, the moment at end 3 of member 6 must be 0. In other words, the moment equilibrium of joint 3 demands there is no moment coming from member 6. There are 2 strategies for making the joints pinned. Either start with rigidly connected joints, then add pins, or start with pins at both ends of all members, then remove one pin at each joint. Starting with no pins is the more intuitive option, but Dr. Jim prefers to start with pins everywhere. You're encouraged to try both strategies to find out what works best for you. Here's how Dr. Jim would go about making the frame pinned. 1. Open the members dialog box and select all the members. 2. Click End Releases and apply moment releases to both ends of all of the members. Now there's pins everywhere. Every joint is a mechanism. 3. Click the Clear Selection button, select members 0 and 2, then click the End Releases button and remove the moment releases. Joints 0, 1, 2 and 3 are now pinned. Joint 4 is the only mechanism. 4. Make joint 4 pinned by removing one of the moment releases at joint 4. We now have a pin jointed frame. Now click the green analysis button, then click the M button to confirm there are no moments in the frame. Then click the T button to confirm there is no shear. Finally, check the LinPro analysis agrees with our hand calculations by first clicking the N button to confirm the axial forces, followed by clicking the R button to confirm the reactions. Perfect, the job's a good un. Well, that's all for today. Thanks for watching. If you found this video useful, please give it a like, and if you don't understand something, add a comment. If another watcher doesn't field it, Dr. Jim will. And remember, learning is a journey. It's transformational. Try to enjoy it. Bye for now. Hope to see you again soon.
Phony numbers.
If I could respond to that.
Let me just tell you what the facts are.